Well, good evening, and welcome to this evening's live presentation on the 2019 REBA Sterling Prize winning Passivhaus residential development at Goldsmith Street. I'm Tony Parasram. I'm the Director of Freeform Consulting. I'm the Chair of the iStruct's Sustainability Panel and the Chair for this evening's technical lecture. We recently had at the institution last month the first of two half-day conferences on climate change, climate emergency. And I raise that because it's driving the conversation, has been for the best part of this year at the institution, with the two-pronged approach, which is use less, embodied carbon calculation, and the sister side to that, which is demand less. And with respect to the demand less, I'd like to introduce our speaker this evening, Robert Scholes, Director at Rossi Consulting Limited, who will be presenting this evening's technical lecture on passive house design at Goldsmith Street. Rob is a Director and Environmental Manager at Rossi Consulting Limited, Civil and Structural Engineers. He's been an iStruct member since 2002, working at the Porter Felixstowe, Scott, White and Hookins, and Richard Jackson Limited, prior to joining Cameron Taylor in 2006. Cameron Taylor went through acquisitions by Scott Wilson and URS before the management buyout of URS Norwich office in 2012 to form Rossi Consulting Limited, of which Rob is a director. Welcome, Rob, and now over to you.
Thank you, Tony, and hello, everyone. Welcome and thank you for joining me today for this webinar presentation on the passive house design and the residential development at Goldsmith Street, as Tony says, which won the 2019 RIBA Sterling Prize for Architecture. I'm aware that many of our guests tonight are not from the institution, and a warm welcome to you especially. I'm also aware that I'm likely to be speaking to a wide range of structural engineers, some of you may have worked on passive house developments, but many today will not and are looking to improve your knowledge on the subject. My aim today is to provide both an introduction and some detail on passive house schemes using Goldsmith Street as an example. For my part, I oversaw the structural design for Rossi Consulting, and we're extremely proud to be associated with the development of affordable housing, which comprises 93 passive house standard dwellings for Norwich City Council and is the largest entirely passive house standard residential development in the country. The fact that this scheme won the Sterling Prize last year is remarkable because Goldsmith Street has a modest scale and nature. It is without doubt of the highest architectural quality of detail and construction, but among the company of Sterling Prize finalists, this had the least architectural drama about it. It has neither the sheer scale of the London Bridge Station nor the complexity of the Macallan Distillery Visitor Centre. The previous winner, for comparison, was a grand office block for Bloomberg described by the judging panel as a tour de force. Goldsmith Street, by comparison, is much more humble in scale and is recognised instead not just for its architectural merit, but also for its immediate relevance to the current issues of fuel poverty, carbon reduction and housing shortage, and it succeeds in pushing the boundaries of the visual appearance of passive house developments. I believe this development has potentially the strongest message among the finalists, and its success emphasises the significance of sustainable development, and in particular housing. There are already signs that the profile of this project and what it set out to achieve is already changing the mindset of some of those who influence local authority housing, and this could be the far more reaching legacy of the project thanks to the RIBA judging panel. For those of you who relish detailed calculations and groundbreaking technical complexity, I'm afraid my presentation won't be going down this route. Goldsmith Street remains a low-rise residential development at heart, but there were a number of technical challenges which I will highlight, but instead I thought this was an opportunity to give an overview of passive house standard construction, its relevance to our collective challenge of meeting the sustainable design standards, and share my experiences of structural design on a passive house scheme. So today I'd like to talk on three areas. I'm going to start with a review of the sustainability challenges that the institution has presented to its members online and through recent publications of the structural engineer. What are the objectives? What can we be doing to change and influence the designs to be more sustainable? And what are the challenges? Well, one approach is a fabric-first design to lower energy demand, and this is where the passive house standard comes in. I want to review what defines a passive house design, how this requirement affects our role as designers, and what we as structural engineers need to be doing to consider during what stage in the design process. I'll look further into this by using Goldsmith Street as a case study to focus on some of the design details affecting the structural engineer and how the requirement for Passivhaus standard affected the design, and asking what more could we be doing to improve our impact on the environment as designers. I hope by the end of the presentation today to have given some insight to the considerations for the structural engineer in entering into a Passivhaus standard design, and how the earliest input into the design and influencing the architect has the potential to ease the construction process, reduce the risk of not achieving key requirements of the Passivhaus accreditation, and generate savings to the client. Any of you that read The Structural Engineer will have noticed a theme to recent publications, particularly the June edition this year, which led with an article by Mike Cook and Will Arnold outlining the institution's guidance on the climate emergency. This listed 6 themes which have been previously proposed in online discussion as listed here. There is more information on these 6 themes on the institution's website or in the June edition of The Structural Engineer, but these themes are bookended by first understanding the problem, by getting informed and sharing our knowledge, and it is in keeping with this that we're sitting here now talking. One of the key problems faced by engineers is the knowledge gap. We're all accustomed to our designs being first and foremost structurally compliant, and we strive to generate efficient designs that are buildable and cost effective. We also design to mitigate safety risks, and these are the primary considerations for every structural engineer. But we need to do more to improve our awareness of the materials we specify. Over the last few months, the institution has produced some excellent guidance documents on calculating embodied carbon, and I'd encourage you to get familiar with these. Our designs have historically been driven by coordinating with an architectural model and achieving an economical structure. Consideration of the hazards and how we design these out are now embedded into our design process, thanks to CDM making it mandatory to do so. Is the reality of the environmental effects of our materials we specify that we have much less bearing on our design choices? What is there to encourage the design team towards sustainable designs, and where the perception is that these will lead to an increase in construction cost? A BREEAM-rated building will always cost more to construct, and these are generally realised only when funding is dependent on BREEAM compliance. The Goldsmith Street residential development is for a local authority, and it is credit to them that they determined to develop these priorities to a Passivhaus standard and put the environment at the forefront of the development agenda. Passivhaus, though, does not require that materials of low embodied energy or recycled or incorporate renewable energy. It focuses instead on delivery of a building which will require minimal energy for heating or cooling. Typically, this amounts to a 75% reduction in space heating requirement. This fabric-first approach is at the heart of what has driven the development of the Passivhaus standard. There is nothing, of course, which prevents such specification of sustainable construction materials, and there is a Passivhaus Plus standard which sets out to incorporate additional requirements for renewable energy generation to exceed the demand. Instead of a requirement to reduce or limit our embodied carbon within the building materials, Passivhaus works from the other end of the challenge of achieving carbon-neutral buildings by reducing the energy demand. For the development at Goldsmith Street, the client's principal target was to address fuel poverty, providing high-quality residential accommodation with a community focus and achieving this through a fabric-first approach. Ultimately, this developed into a Passivhaus standard criteria to address the fuel poverty problems facing an increasing number of social housing tenants. To summarise, despite not needing to provide renewable energy, the use of Passivhaus standard helps significantly with meeting the 2050 carbon neutral target by reducing the amount of demand, and this is significantly easier to achieve economically when the demand is so much lower by the use, for example, of roof-mounted PV panels. So let's have a closer look at what is involved with meeting the Passivhaus standard. The term Passivhaus is misleading, as it's not limited to just housing. It is a concept originally defined in Germany in 1996 and sets out energy performance criteria for any building type. It does not, however, define standard details or forms of construction, as we're used to seeing, say, with robust details, and these criteria are summarised on the slide. Passive House is growing in popularity in the education sector, where it's been demonstrated that students show greater sustained concentration levels due to the higher quality of air with lower carbon dioxide levels. There are over 20 Passive House certified schools and education buildings in the UK, with more in construction at the moment. In other sectors, we now have Passive House standard offices. A Passive House swimming pool is being constructed in Exeter, and there's a Passive House hospital in Germany. China is currently using the standard on a vast number of residential developments. This is an approach which has great potential for our future built environment on a global scale. So for those of you who have not encountered Passive House design, these criteria will be required to achieve the standard, and the project needs to be independently validated by a certified assessor. There's an emphasis on both design and construction in order to achieve the standard and the principal criteria. And this is where structural engineers and their fellow architects and design consultants have to consider the following 5 characteristics of Passive House design. And these are the design cornerstones of achieving economical Passive House accreditation. The first is a high specification of air tightness. In the construction industry, we're accustomed to requiring a value of around 5 air changes per hour for a typical build specification. Structural engineers tend to be less involved with considering this requirement, as air tightness is typically achieved through architectural detailing and construction good practice, often with the contractor needing a few cans of squirty foam and tape on hand. But this approach isn't going to cut it to achieve Passive House standard, where a maximum of 0.6 air changes per hour must be achieved. It requires a great deal more coordination with the architect on how these details can be achieved, and without good detailing and a rigorous specification, it is likely that the contractor will encounter failures. The more complex and bespoke the detail, the higher the risk of problems and delays in building them. Simplicity of detail is usually the key, and without stifling the architect's creative flair can be the structural engineer's challenge. The next is the insulation thickness. It's typical for Passive House external walls to be around 600 millimeters thick to achieve the required U values. This will have an effect on the structural components such as the foundations and outer leaf stability. And if there are high loadings through the inner leaf, the engineer has to be mindful of eccentric loading going into the foundation. The outer leaf has to be tied to the structural zone for restraint without causing thermal continuity across the cavity. And once solar shading is incorporated too, this can also present challenges. One area which causes the most headaches for both the engineer and the assessor is the inclusion of thermal bridges. And this is one of the key challenges that Passive House design presents to the structural engineer. Even with the most straightforward architectural approach with a uniform superstructure, the engineer is presented with the problem of how to provide structural continuity into the foundation without causing thermal bridging. In most forms of construction, a structure will provide a direct connection between the superstructure and the foundation. Think of a steel column base plate onto a pile cap or pad, or masonry wall bearing onto a strip foundation. These tend to be the points of maximum load concentration, and instinctively, structural engineers want to detail a robust and direct structural arrangement at this most critical point in the load path. But this isn't a compatible configuration with Passive House certification. Cantilevered balconies, discontinuous brickwork facades, terraces, solar shading, they also all pose similar problems, but the engineer is generally more accustomed to thermal breaks on horizontal cantilevered structural components. Generating this thermal separation is the primary consideration for the structural engineer in designing to Passive House standards. Fundamental to the operation of any Passive House building is the use of a mechanical ventilation heat recovery, or MVHR system. This system extracts air from kitchens, toilets and bathrooms and provides fresh air to the living areas and bedrooms. The air is filtered and passes over a heat exchanger through a ducted system, the likes of which you wouldn't otherwise see in residential accommodation. As you'd expect, this requires closer coordination between the structure and the services engineer. Nobody wants to see bulkheads and boxing around ceilings in their home, so the floor and roof zones may result in a carefully designed joist and duct layout. The fifth and final characteristic is solar gain. This is a benefit to Passive House buildings during colder months, which provides free warming energy. but can be problematic during the warmer seasons, leading to overheating unless it's managed. Building orientation and careful detailing of window sizes and solar shading is absolutely crucial to managing this, but tends to be determined by the architects and planners, but we can help inform and influence this at the outset. For all these factors, the Passivhaus standard should be established as a requirement at the earliest stage, and the designers accommodate the specification into their design from the start. Similar to BREEAM, it's not easy to bolt on compliance with the Passivhaus standard because fundamentals such as the orientation of the buildings, external materials, building massing, and through to the building details will determine how easy this is to achieve. One obstacle to the wider use of Passivhaus is the associated cost of construction. Costs can be expected to increase for components like windows, which tend to be triple glazed, insulation, which has so much extra thickness, and the costs associated with building to a higher specification compared to a traditional construction standard. However, it's important to realise that these costs can offset some other components. It reduces a requirement on the thermal plant, a reduced reliance on renewable energy, and if designed well, construction detailing should be simplified by repetitious and rationalised to reduce complex details. While preparing for today, I asked the Passivhaus consultant from Goldsmith Street what he would say to an audience of structural engineers, and his message was this: to give the contractor the best chance of achieving the airtightness and avoiding cold bridges, to reduce the risk of not meeting the criteria, to mitigate the cost uplift and to achieve the standard, the structural engineer must understand these 5 principles and influence the architect to simplify and rationalise the form and detail of the building. And this message is absolutely at the heart of good Passivhaus design. Publicised figures suggest that the Passivhaus standard can be achieved for a premium of 5 to 10% on the construction value, but largely on the proviso that the design team, designing from the outset with Passivhaus in mind, and have the characteristics and criteria that we've just reviewed at the forefront of their minds throughout. So, with our 5 primary design characteristics of Passivhaus standard firmly in mind, let's look at our residential development at Goldsmith Street in Norwich. This is a brownfield development of 93 dwellings for Norwich City Council, all of which are to Passivhaus standard, and on completion was the country's largest fully Passivhaus certified residential scheme. It's located about half a mile west from Norwich City Centre within an urban residential setting. The proposed development is split into 7 blocks comprising 2- and 3-storey terraced houses, with 3-storey apartments bookended to each of these blocks. The blocks are orientated such that the main elevations are south-facing. These terraces are typically around 50 metres long, and the northernmost terrace pictured here is around 130 metres long. And this became a consideration in selecting the most appropriate structural concepts, in particular the foundations. This typical section through the terrace blocks gives an idea of how the blocks of housing relate to the seasonal sun positions, and also give a sense of the scale of the development, eaves heights, and the relationship of the buildings to each other. You can also see the non-uniform configuration of the roof profiles and how the upper floor ceilings follow the roofscape. The architectural vision was a return to the Victorian model of an inclusive terraced community with inward-facing back gardens. Mikhail Rich's architects won the architect's role through a competitive basis and developed the massing and planning drawings in advance of the appointment of the rest of the team. Key players on the client team are listed here, and the contract was won by local contractors R.G. Carter on a single-stage traditional procurement contract. The contractor was selected on the basis of the most competitive offer and ongoing experience of Passivhaus developments using a fabric-first approach. The requirement to meet a Passivhaus standard requires a very high level of construction control and monitoring to achieve the stringent high air tightness. During the tender interviews, the contractors were required to demonstrate how this would be achieved. Carters were able to show that a dedicated air tightness champion was proposed as part of the team, and this was a key presence on site during the construction of Passivhaus standard buildings. Their role is to understand how the architectural detailing of the vapor check membrane was proposed through regular on-site workshops with the architect, followed up by toolbox talks to present this to the operatives, who would in turn be constructing the detail, and they would then monitor the progress on site during construction. Progress was also closely monitored by the client's clerk of works, who provided weekly reports. The development was not originally conceived as a passive house development at outset in 2008. The decision for Passive House standard was sparked by a number of factors, partly the duration of the lead-in process, during which cases of fuel poverty were an increasing factor, particularly during national recession. In response, Norwich City Council started the introduction of fabric-first energy efficient housing on other sites, leading to the requirement for Passive House standard at Goldsmith Street. But the format of the buildings had already been defined, and while most of the terraces were readily adaptable to Passive House standard, it was soon clear that the length of the terraces and the balcony arrangements of the three-storey apartments pictured here were not particularly easy to detail. The architectural proposals pushed the boundaries of what can be visually achieved with Passive House housing, and this wasn't without some challenges for the structural design. So moving to the structure at Goldsmith Street, we have a timber frame superstructure on strip foundations with a suspended ground floor slab. The choice of superstructure was determined very early on. The elevations are generally of brickwork outer leaf facing the streetscape and rendered to the rear elevations. A feature of the main elevations is the high frequency of large window openings, nearly full height openings level with the door head. The small panels of masonry between the windows are not well suited to load-bearing masonry construction, and the resulting lack of robustness by stack bonding the inner leaf would have led to a large amount of secondary framing. After trialling a number of structural options, it was soon apparent that a lightweight frame would be the most appropriate for this arrangement, and this resulted in a timber frame being adopted. This approach was also provided for a lightweight sustainable material for the superstructure, which was compatible with our first approach for the foundation proposals. It is quite typical for passive house structures to include a raft foundation with rigid insulation, which provides all sorts of advantages, which you'll see on the next slide. However, foundation specification is dependent on the choice of facade finishes and, of course, the prevailing soil conditions. Going back to my earlier comments on preventing a vertical cold bridge at the base of the superstructure into the ground, this is a pivotal design decision. However, this ended up being changed from a raft to a strip footing and providing a suspended precast ground floor. To understand the reasons behind this structural format, a quick overview of the site's history is needed, as this had a significant effect on the design of both the substructure and the superstructure. Goldsmith Street's urban setting had originally been developed for light industrial use and then subsequently redeveloped as low-rise housing stock, so the shallow soils had been worked and disturbed. Typical for Norwich, ground conditions comprised about 1 metre to 1.5 metres of made ground over undisturbed loose to medium dense granular soils over weak chalks at depth. Finally, due to its locality to the original old Norwich railway station, the neighbourhood had been bombed during World War II, and there was a residual moderate risk of unexploded ordnance, or UXOs. So prior to receiving the UXO assessment, our approach was to improve the upper soils using vibrostone columns with a ground-bearing raft to support the timber frame, and an independent shallow strip footing to support the outer leaf. The use of soil improvement is commonly used on granular brownfield sites and overcomes the variability caused by disturbed soils from previous development, and would allow for economical mesh reinforced shallow foundations to be used where deep footings would be at greater risk of collapse due to the prevailing loose granular soil. This arrangement also provides a ready separation between the outer leaf and the internal structure by providing regular load-bearing timber frame walls supported on the raft, built off structurally rated insulation. The benefit of this approach is that there's a robust thermal break provided below the reinforced concrete raft across the entire building footprint, and internal load-bearing walls can be used frequently for an economical superstructure without compromising the thermal separation between the superstructure and the supporting soil. It's worth noting that if you're using this method, the structural insulation layer that is typically specified as 300 mm thick and the structural rating needs to be carefully specified with this in mind. The structural rating for the insulation is only a strain rated figure, and the pressure rating is usually associated with the loading at which 10% strain is achieved. On such thicknesses, a greater rating is required to limit the overall compression under loading to an acceptable figure. On the example shown here, the same pressure of 50 kilonewtons a square metre is applied to the same rigid insulation rated at 150 kilopascals, but of differing thicknesses. The top example for a 75mm thickness of insulation has a calculated compression of 2.5mm and could be accommodated. But by increasing the thickness to 300mm, the calculated compression of 10mm would be excessive, and further consideration of the specification would be needed. There would of course be some redistribution of the pressure through the slab stiffness, but during the Goldsmith Street design, the specification of increased structural rating for the insulation had to be increased. However, once the UXO risk had been established, the only way that vibrocompaction could be considered was to use magnetometer probing to confirm the absence of potential unexploded ordnance, and this carried a 5-figure premium and became prohibitively expensive to the project as a result. A raft foundation on unimproved soils was also considered, and this can be a valid structural option for looser soils, but the loose and variable nature of the soils was simply not compatible with the proportions of the building footprint. As seen earlier, these are long and thin on plan, and with the fenestration arrangements would be particularly susceptible to cracking of the brickwork, so we worked with the contractors to develop an alternative approach. The revised design of the foundations followed a more traditional approach, with insulated beam and block suspended ground floor and deeper strip footings. This consisted of 150mm thick beam and block zone with insulation infill blocks and 225mm of rigid insulation above, with a 75mm of fibre reinforced concrete topping, and these typically span the width of the terrace house units. While saving on UXO testing, the effect of this revised arrangement not only increased the volume of arisings and imported concrete, but also wasn't as favourable as the Vibro Improved raft for 2 further reasons. First, the superstructure was affected as the internal load-bearing lines couldn't be supported on the structural slab. So without intermediate supporting partitions, the first floor had to be redesigned with increased capacity to span the full width of the unit. Secondly, there is a more direct thermal route through the structure to the ground, so low thermal resistance perinsul glass blocks were required at the bases of load-bearing walls as a thermal break. Care is needed here, as although the perinsul HL units have a compressive strength of 2.75 newtons per square millimetre, the units are only 65mm high, and this leads to a reduced unit strength value, which isn't suited to concentrated loads. You can see the foam glass block course on these drawings, on this photo here, at the base of the party wall, and these have been set out above the finished beam on insulated block level. Moving to the superstructure, the timber frame for the majority of the construction was relatively straightforward and was manufactured and installed by a specialist subcontractor. The inner leaf is not so different to traditional stick-built timber frame house, with an 89 by 50mm internal load-bearing studs on the external and party wall lines, and engineered timber joists at first floor and roof level. Roof joists are typically 400mm deep, extra deep partly to provide room for the additional insulation, and the first floor joists are 240mm deep. These joists needed to be coordinated more closely than standard housing, with the much larger MVHR ducting that you see here, especially within the floor zone. The external wall construction is rather different to standard construction though, as these need to generate a cavity of some 350mm, which is filled with blown insulation and provide restraint to the outer leaf. This is achieved by providing OSB fins fixed to the sides of the load-bearing studs, and then a smaller outer stud provided to these, which provides for another OSB lining on to the outer leaf. This is used for fixing standard timber frame masonry ties to provide restraint to the brick outer leaf. The photo shows the external wall construction prior to the fixing of the outer OSB sheathing and membrane. While the majority of the terraced housing was readily adaptable to Passivhaus, the three-storey apartments to the block ends were less straightforward, and these needed more detailed structural coordination to meet Passivhaus requirements for thermal separation. To minimise costs, conceiving a Passivhaus economically typically imposes limitations on the architectural form. I'm going to touch on three areas which cause some design and buildability challenges, and how these were addressed on this project. First, the outer brickwork envelope doesn't align vertically down to the foundation and is set back over the internal structure. This may have not been such an issue if the facades had been rendered or clad with material which was fixed directly to the inner leaf structure, but a masonry brick skin was a requirement and it needed its own independent support. Careful consideration was needed here to prevent cold bridges between the brickwork, the steel supports and the internal spaces. As brick slips weren't an option, the configuration needed a combination of secondary steel goalposts to support the main panels and hot-rolled steel box section lintels to support the upper panels of masonry. The goalposts were located fully within the thermal envelope, so these were effectively warm structures, and the posts bear onto low thermal conductive structural blocks. The brick panel is separated thermally from the steel goalposts to prevent cold bridging between the brickwork and the steel posts. The lintels, on the other hand, though, are located within the cold zone, and these didn't require this approach. In the photograph here, the panel to the left is supported on a warm goalpost, and the narrow panel facing you is on a cold lintel. This arrangement also needed very careful coordination in order to function as a structural balustrade, made more difficult by the large cavity to the external wall, effectively removing the internal structure as an option for restraint. The perforated brick balustrade was ultimately achieved by using resin-anchored stainless steel threaded bars within the brick balustrade and post-tension through pre-drilled brick units with a structural cap plate to the head of the balustrade wall. This cap plate acted as a horizontal beam with restraint at each end from the abutting panels of masonry. This was particularly challenging in construction due to the necessary coordination needed. For the size of cavity, outer leaf masonry bridging the cavity even though it needed its own lintel, and these needed bespoke detailing and manufacture to suit the proposals. While none of the above was too much to achieve, these balconies would have been near the top of the list of configurations to review to simplify the construction, and would have been simplified if a lightweight cladding or render system is specified. Another challenge, which is by no means unique to this project, is the fixings for the brise-soleil solar shading. Solar shading is a common feature of Passivhaus buildings, but again presents a structural engineer with a problem of how to prevent a cold bridge. Typically, a thermal pack will be sufficient with a rigid connection through the external envelope of the building. However, the large insulated cavity is too remote to the external leaf, and the fixing is based on the outer stud line within the cold zone. This outer OSB lining was reinforced by the timber frame manufacturer above the south-facing windows, and rigid steel cleats were bolted to allow connection for the solar shade. However, due to the relatively accessible positions of the ground floor brise-soleil, there was a concern that these could be vandalised or susceptible to overloading. The brise-soleils were architect specified, of aluminium construction and deliberately lightweight in nature. While able to withstand naturally arising events such as wind and snow, these would not be up to malicious damage or excessive loading through misuse. In the event of a bracket failure, the primary bracket fixings would not be accessible, and so a hierarchy of structural resilience was established, which increases in strength from the outside, moving inwards, such that in the event of solar shading being overloaded, the first point of failure would be a connection that would be accessible and maintainable. The client wanted this confirmed by demonstration, and a test rig was trialled on site and loaded to failure, which as designed was of the external bracket framing. The unit was then unscrewed from the outside and a replacement unit reinstalled. One final area that led to some awkward detailing was the relationship between the floor levels and ground levels. The architect wanted to avoid ground levels stepping up and down on the long elevations relative to the front doors, which needed to be flush and level. This was an issue which was difficult to avoid, particularly in places where the front doors were being directly accessed off the pavement. With a timber frame superstructure, there needs to be vertical separation between ground level and the sole plate, and this led to the introduction of a 225mm high blockwork step under the sole plate, and a complication in the thermal connection and vapor control layer at this point. Because wind loading is transferred vertically by the structural studs, this causes a horizontal reaction at the head of the block upstone wall. As you can see on this photograph, the blocks which kick off the structural slab level are already 300mm tall to reach the finished floor level. This is due to the thickness of insulation and composite floor finishes, which you can see is the height of the internal blockwork wall shown here. These then had to be raised a further 225mm to provide the vertical separation from ground level to the sole plate, and ended up needing to be 215 thick block for the necessary stability. So from the development, I think these three items, the floor levels, solar shading and the step masonry panels, are the main areas I would flag as items to concern early in any passive house development, and I'd urge you to review these sorts of items with the architect at the earliest stages. So moving to our closing thoughts for today, for Goldsmith Street, could more have been achieved, and what lessons were learned? Well, the scheme has been received as a success by the construction industry and recognised in the highest possible way by the RIBA last year. It has clearly inspired other local authorities to look at how future housing stock, social housing stock, is delivered, and this, in my opinion, is the project's greatest success. The brief has to drive the decision to build Passive House, and in the broader picture, this is a clear way to delivering net zero carbon buildings by 2050. Without Norwich City Council's decision to demand Passive House, we probably wouldn't be discussing it here and now. Following this being defined in the brief, we need to bridge the knowledge gap in consultants and be designing Passive House projects that have synergy with the 5 characteristics of Passive House design, namely no thermal breaks, increased insulation, achievable air tightness, allowing managed solar gain, and a coordinated air supply and extract system. Some details on this project certainly presented some challenges, and I hope that in sharing these today, these experiences will benefit the wider promotion of Passive House standard design and development. My advice, and that of Passive House consultant from Goldsmith Street to anyone about to embark on a Passive House project, is to work with the design team to keep the details simple. More can be done in our pursuit to improve the sustainability of our built environment. For example, Goldsmith does not have PV panels or other renewable energy options to further improve its performance. And although there were measures taken to improve carbon content by using cement replacement, and we undertook a lot of recycling of demolition arisings on the project, the materials it's made of were driven more by efficiencies than environmental impact of the construction material. But everyone involved with the project will not be surprised to see future Passive House projects rolled out in other local authorities who build on the success of Goldsmith Street and incorporate these wider sustainability factors in too. The institution is currently doing a great deal to improve sustainability knowledge through a number of committees promoting Declare, which is seeking support from industry and individuals, and I would encourage you to join them. My final slide here is a link to this, and also to the 6-point initiative by the institution's Climate Emergency Task Group, which we looked at earlier. The institution has also released guidance to structural engineers on calculating embodied carbon, and it is through these that I hope we will fill the collective knowledge gap. Improving our understanding of sustainable design and our design processes within our control. The challenge will remain that the client needs to lead the way, as has been demonstrated by Norwich City Council at Goldsmith Street. Thank you. I hope you found today's presentation of interest, and many thanks for your attention.
Well, Rob, thank you very much for that. Excellent presentation on the award-winning Goldsmith Street, and a lot packed in there for us to consider with Passive House. We've got a few questions. We're going to move on to questions that have come in, and from Nikos, first of all, with global warming, it might become more common to try and keep the heat out rather than keep the heat in. How does Goldsmith Street accommodate the potential for global warming effects?
I think, first off, I'm not an environmental consultant on that one, but the message with Passivhaus is through the air tightness and the increased amount of insulation and the solar control, it is very much about keeping a uniform temperature within the building through that insulation and those processes. So it should achieve those criteria as well. I did mention on the closing slide, I've put a link there for the Passivhaus Trust, which does have quite a lot of information on that. So I think it's as equally as applicable to warmer climates as cooler, for sure.
Okay, that's great. Moving on, we've got one here about easy joists from Georgios. You didn't specify easy joists, or at least it didn't come across in the presentation. You specified easy joists in order to accommodate the ducts through the structural floor zone. Was it down to cost, or was it not a necessity?
Yeah, I've certainly seen those, and that could be certainly a way to ease the coordination of the two. I wouldn't be surprised if they had been used. Ultimately, it was a subcontractor design within the contract. It does bring to light actually one of the a challenge that I didn't really dwell on there, but because it was developed as a traditional contract, and I'm sure many people listening will have come across this, having a traditional contract where there's a principal structural component which is specialist designed, you're left with the challenge of how you manage a subcontractor but need their detailed design input at an early stage. So because of Passivhaus does place emphasis on a coordinated design, a closely coordinated design, that is definitely a difficulty in how you procure the design services of a subcontractor, and that was done through a reduced brief, if you like, for a specialist subcontractor who was promoted to the contractor to take on as their subcontractor. But as it turns out, posi joists could have been used. It was just that this particular timber frame manufacturer didn't choose to use them.
Yeah, it's good to know it's an option. We got another one here from Mick. Would you remove the balconies if you could next time? It seems this is a cost driver. If there was an option to remove them, would you save what could you save if you didn't do this? Yeah,
I'm not sure I can answer what in terms of structurally what we could save. It would have. I think there's a team of contractors of builders who worked on this project who would be nodding furiously at this point. It was definitely a challenge, and I think that's come across really. I think with Goldsmith Street, because it was conceived prior to being defined as a Passivhaus project, that is one of the sort of legacies of what it was. We explored a number of value engineering options, and that was explored, but that it basically wasn't on the table as an option because of planning. It was too far down the line. It presented a problem. If you can get vertical alignment of the outer envelope, it's definitely a way forward. And if balconies are needed, then independent structural framing is definitely a more conducive way to do it, and that would have certainly improved the buildability. As a halfway house, then a outer leaf that can be fixed back, as a regular cladding to the outer leaf, rather than needing its own support, it is probably the halfway house. But really, to drive the most economy in there, and I think this is the challenge for structural engineers we often face, and I suspect there may be some architects online today, that we work together to bring value, but the architectural vision is really what we're trying to meet. And that's one of the challenges really with Passivhaus is good value is going to follow a simpler form. It doesn't. The architectural approach has to be slightly different in as much as it has to acknowledge the presence of Passivhaus and the requirement for it, and work with that to really achieve the best value and get the best result.
That's great. We've got one here which is really quite a current day question given the high timber content in Goldsmith Street. What fire safety or fire engine? This is from Liam. What fire safety or fire engineering solutions were used? Did the high thermal ranges of the floors and doors provide good fire compartmentation between the rooms and the other properties?
Yeah, yeah, that's definitely topical, and there's been a lot of movement in industry on fire since Grenfell, but the design and specification was part of that. I'm not sure I can say much because I don't know beyond it was compliant with the building regulations, and it was primarily achieved with I think plasterboard and fire line fit out. Every dwelling had to be completely enclosed, but that's probably one I would leave to the architects if they were here to respond on that one, I'm afraid.
No, that's fine. That's fine. And yeah, I think there certainly was cladding and the gyprock cladding that went on that would have afforded a fire rating. Chloe got a question here on PVs. Would retrofitting PVs or photovoltaics be possible at some point, or would this compromise the air tightness of the current building?
Okay, so the air tightness is generated really within the inner lining of the Passivhaus section. So working inwards, you've got your outer cladding, and then the next thing you'll see is an OSB. Is a vapor check, a breather membrane. Then a lining of OSB, which is fixed to if you effectively stood off from the main structural line by those fins that we saw. Inboard of that, you've got the structural studs, and then fixed to that is another layer of OSB and a vapor control layer. So you've got a substantial amount of build up before you sort of reach that all-important vapor control layer. So that's more on the inside face. Loading-wise, there's provision for the panels, but that is something that I believe could be fixed in there.
Okay. It's generating quite a lot of questions, this one. The popular presentation there, Rob. We've got one from Kush, which is, did the insulation blocks at the base of the walls decrease the design life of the walls? And is there a specific maintenance regime required generally for the different structural systems being implemented, or is it much the same as a normal structure?
Okay, so I think we were talking about the parental blocks there. So it's a lot of the structure underneath the timber stud there was thermalite type of aerated block. I remember exactly which block manufacturer was used, but it was a aerated block for improving thermal resistance, and that then needed to sit on a 65mm high parental block unit there. That is capable of that's up to the job, if you like, of a timber frame stud wall. But as soon as things and we put that at the bottom, of course, so that there was some load distribution through, if you had cripple studs or concentrated loads coming through multiple studs supporting beams, there would be some load distribution through the upper layers of 7N aerated block work before they hit the parental block. And as I mentioned, that's because it's a shallow unit. You you lose something in the structural performance. But the stresses were sufficient sufficiently low that wasn't a problem. Where we had the goalposts, though, the steel goalposts, which were bridging the rooms and effectively threading their way through internal partitions to support masonry panels above, they couldn't sit on those principal blocks. They had to be sort of factored in, if you like, to the thermal model that the Passivhaus consultant was using, and that was they were bearing straight onto 7 Newton thermalite blocks, which had its own issues really, because they don't like to be drilled, and anchors were a bit of a concern there. But yeah, we found a way to make that detail work.
Excellent. Another one here from Michael. Does Passivhaus design always require a thermal break at foundation level, or are there means of avoiding this, particularly if higher loading from the superstructure is applied?
Yeah, this is a good question, and as I said, I think that's probably the biggest challenge we have. Instinctively, we want to, the last place we want to be breaking the structure is at the connection with the foundation. That's really the advantage. To answer the question, yes, you do. You need that separation. So if you've got brickwork, that needs its own foundation, or some separation from the main structure. Otherwise, your slab is effectively I almost look at the building like a fridge or a freezer, that you've got this space within, and then it's completely enveloped in an insulation right through to and the structure sort of sits beyond that. So the framing something does start to present some challenges where you've got concentrated loads and how they're achieved. We really didn't end up going there, I suppose, with Goldsmith Street, but it's certainly a consideration. You're going to have to start introducing thermal packs of a higher, next level up than glass blocks, which to take those loads from column base plates. As it was, we ended up using. We had effectively compensated the thermal performance elsewhere in order to allow these these individual components to come through, but they were relatively light loads in terms of column reactions, so we could take those down onto thermalite blocks.
Okay, just a couple more questions. We've got one here from Joel, which is, on a small scale project, how would you manage the structure, services, architecture coordination if BIM is not used?
Okay, so we didn't have BIM on this one. It does need managing. So I think it depends on the complexity of the project. There's always quite a bit of ducting going on. If we're talking about the floor joists, that's certainly something that needs close attention. And we were lucky on this project that we had such dedicated architects. They drew out everything. They effectively did the job of a 3D package anyway, by the level and quality and quantity of the drawings that they produced. So an awful lot of things were considered in a great deal of detail. It does need close managing, and it's like all coordination. It's hard to put a figure on how much time or how much it's going to cost to achieve that. BIM would certainly help. BIM isn't, 3D coordinated models aren't a common feature of low-rise housing at the moment. We do see it occasionally, but that's certainly something. I think that the bigger, when you start scaling up the size of the development, BIM is certainly going to help. On a smaller scale development, then I think just more. It just needs more consideration. But certainly, walking into a Passivhaus design, knowing what to look out for is a definite advantage. And really that's what I thought. Well, I hope some of the things that have come from this are worth sharing, and you certainly want to do your bit as an engineer, as a fellow designer with the rest of the design team, to say, well, look, hang on, we don't want to overlook this. That problem's going to give us a bit of an issue. Can we just try and rationalise it? And like all value engineering, it's best done and most effective done the earlier that you do it.
Yeah. Just a couple more, and for this evening, we've got one here from David, which is, will you be able to share some of the structural details on a public database, e.g. the Passivhaus Trust, or low energy building database? Is there such a place to share this?
I'm in touch with the Passivhaus Trust, so I think that's something that we can certainly talk to them about. There's a sort of a number of things to sort of think about on that one, I suppose, but there's certainly sort of ways I could speak to them and just see if there is a knowledge pool that we could pull together. The thing is, I think if we if we collectively do these key first decisions, then the projects get more economical, as I say. So there's definitely some value in there, in the interests of promoting it. Passivhaus doesn't fit all projects. I didn't go there with a statement like that. It's not going to suit every single condition. But there are a few sort of myths out there that it doesn't have any fresh air and it's not suitable for. But it does provide, especially in education buildings, a very high level of environment and reduced levels of carbon dioxide, because the air is managed in a way that you don't typically get in natural ventilated buildings. But the cost premium, like all sustainable development, is the one we've got to find a way around, really. And I think the more common something is, the more the norm that a construction process comes, and the more understood that, say, construction details like that are understood. Hopefully that will have some bearing. So now I'll be talking to our friends at Passivhaus Trust about that.
Excellent. And lastly then for this evening, where can we find, this is from Zainab, where can we find the guideline for the Passivhaus standards?
So I've got, sorry, my computer's gone to sleep now, but I presume on screen we've got the links that are on there. So that the Passivhaus Trust website is an extremely good place to start. There are all sorts of documents on there about what to look for in Passivhaus design, what makes Passivhaus design, where you can use it, who's building it, and all kinds of case studies. So I would say that is a very good place to make a start there, that should be a really good source. That is a really good source of information about what makes Passivhaus, and some case studies there.